Hello everybody, welcome back to Controlling the BBT playlist. In the last video, we have seen how the P controller wasn't suitable for the BBT system. Hence, in this video, we are going to design and implement other types of controllers, which are the PD control and the PV one. Let's start with the PD controller. With respect to the proportional controller, we are adding the derivative action, which means that we are adding a zero to the system, though we are not changing the order of the system. Typically, this controller makes the system faster, but it also introduces an undesired effect called derivative kick. And for this reason, it's almost compulsory to add a low-pass filter. In our design, we will make use of the academic form, so our design variables will be the controller gain and the derivative time constant. The effect of the filter instead will be neglected in the design phase. Let's insert it into the block diagram and let's compute the closed loop transfer function. We can see that we still have a third order transfer function. This time though, we have introduced a zero. Let's focus on the denominator, which is also known as the characteristic polynomial. It is a third order polynomial. Here, the challenge is to find the design variables which satisfy some performance requirements. But when we talk about performance metrics, we have referred to a second-order polynomial. And we were acting on the two parameters, which are the damping ratio and the natural frequency, that determine the dynamics of a second-order system. How can we compare a third-order polynomial to a second-order one? The smart trick is to write our third-order polynomial as a product between a first-order residual polynomial and the desired second-order polynomial. At this point, we can set the requirements, for example, in terms of percentage overshoot and settling time. From these requirements, leveraging the expressions we came up with in the performance metrics videos, we can retrieve the damping ratio and the natural frequency. So, we have obtained the value of the damping ratio and the natural frequency, but indeed, we are looking for the control gain and the derivative time constant. How can we get them? It's quite simple. We can set a mathematical equality between our original third-order polynomial and the product of the first-order and the second-order polynomial. And from this equality, we get the value of the coefficients of the residual polynomial, but most important, we get the controller gain and the derivative time constant. All the numerical computation have been performed in Compose. So let's open the Compose script, which also draws the root locus and computes the step response of the linear model of the BBT. Let's run it. We can see that, in fact, we get the same values that we have reported in the slides. If we look at the root locus, we see that there are 3 poles and 1 zero. All the 3 poles lie on the left half plane, which means that they have negative real part. Hence, the system is stable. The pole which is far on the left on the real axis is the pole of the residual polynomial. Since its real part is way bigger than the real parts of the other 2 poles in absolute value, its related dynamics can be neglected. It is important to notice that also the zero lies on the left half plane, and soon it will be clear why we made this consideration. Now let's have a look at the step response. This time, compared to the P controller, we are able to move the ball to a certain position. And we can see that the settling time is roughly 2 seconds. But the percentage overshoot is way bigger than 2%. It's roughly 20%. Have we made any mistake in our design or in the script? No, we have made it right. And let's figure out why we are getting this overshoot. We can manipulate a little bit the closed loop transfer function. As we have said before, we can neglect the residual polynomial dynamics and we can manipulate the denominator as well. At this point, we can leverage partial fractional decomposition to write the transfer function as the sum of 2 transfer functions. And we can see that the first transfer function is the typical transfer function of the second order system we have studied in performance metrics. while the second transfer function is the scale derivative of the second order system transfer function. This means that also the step response is determined by the sum of these two transfer functions. Instead, during the design phase, we have implicitly considered only the contribution of the first transfer function, neglecting the effect brought by the added zero. Moreover, we can see that the contribution of the second transfer function is weighted by the value of the zero. In general, a left half plane zero makes the system faster. But if z increases too much, which means that the zero moves far to the left, then the contribution of the derivative term decreases. In our case, if we look again at the root locus, we see that the zero is not far on the left. This means that also the second transfer function is contributing to the step response, and so we are getting an overshoot greater than what we have designed. This also means that the mathematical method we have used, even though it's extremely elegant and simple, is not suitable for properly designed PD control. But for example, it can be used to find the initial value for an optimizer, which eventually will produce the right controller values, as we will do in another video for a different controller. Finally, for the sake of completeness, let's mention what happens with a right half plane 0. A right half plane 0, which means a negative value of z, makes the system slower and might cause undershoot. Now, before moving to the next controller type, let's deploy our PD controller on the real BBT. And let's open Activate. In this model, there is both the real plant and the linear model. Inside the controller block, we see the PD controller, implemented with a PID block setting the integral gain to 0. And the proportional and derivative gain are defined in the initialization tab. Moreover, in this block, we have to define the low-pass filter of the derivative branch. Let's run it. We see that in the real case, there is almost no overshooting due to saturation and non-linearities. Also, in the linear model, the overshooting is smaller than expected. In fact, if we look at the controller command, after the saturation block, we can see that due to the derivative kick, saturation occurs. This means that the servos are driven to an angle which is smaller than the one provided by the controller without saturation. Moreover, if the calibration procedure has been done properly, the steady-state error in the real case is roughly 0. We have seen as the PD derivative control turned the BBT system into a fast and stable system. But the derivative kick can be troublesome. Hence, let's move to another type of controller, the PV one. Also, in the PV control, we can see that there is a proportional and a derivative action. But the derivative action is now placed in the feedback path. The input of the derivative action is no more the error between the set point and the present value. Only the present value, that in our case is the ball position, is taken into account by the derivative action. This means that the sharp changes in the set point which cause the derivative kick in the proportional derivative controller are no more troublesome in the PV controller. This controller, in fact, is not affected by derivative kick. But of course, it will be negatively affected by measuring noise, whose effect can be reduced with low-pass filters. Moreover, since the derivative action is placed on the feedback path, the PV controller does not add a 0, and it acts as a virtual damper. Now, let's design it, and let's compute the closed loop of this block diagram. We make an intermediate step, which is the computation of closed loop transfer function of the inner loop, and then we can easily compute the closed loop transfer function of the whole block diagram. If we look at the denominator of this transfer function, which we remember is the characteristic polynomial, we can see that it is of the third order, and it is the same of the one we have obtained for the proportional derivative controller. This time, though, there is no 0. And it follows that to design our controller, we can use the same technique. But this time, since there's no 0, based on the reasoning we have done before, we expect the overshoot to be the same as the one we are setting in the requirements. Also here, all the computation has been done in Compose. So let's open the script and let's run it. From the root locus, we can see that there are 3 poles and no 0. Since the characteristic polynomial is the same as the PD controller, also the poles are the same. Hence, we can make the same considerations. The system is stable because all the poles lie on the left half plane, and the pole of the residual polynomial is far on the left, so its dynamics can be neglected. Now, let's have a look at the step response. The settling time is roughly 2 seconds, and this time, since there is no 0, the overshooting is 2%, as we have set in the requirements. We can notice, though, that the system is lower, since the rise time is bigger compared to the PD controller. The system behaves like the second-order system we have studied in performance metrics. In fact, if we look at the transfer function, neglecting the residual polynomial dynamics, since its pole is far on the left, we can rewrite it as a second-order transfer function, which has the same shape as the performance metrics one. Now, let's deploy our PV controller on the real hardware, and let's open Activate. Inside the controller, we can see the PV control, with the proportional action and the derivative one. Also here, there's a low-pass filter to smooth out the noise coming from measurement that will negatively affect the derivative action. And as done for the proportional controller, we haven't taken the filter into account during the design phase. Let's run it. We can see that the real system response is pretty similar to the PD control one, just a little bit slower, and it does not exhibit overshooting. Also this time, the linear model shows an overshooting different than expected, but the reason is not the saturation. In fact, there's not the derivative kick, and the controller does not saturate. The difference is due to the low-pass filter that wasn't considered in the design phase. As with the PD controller, if the calibration is performed correctly, the steady-state error should be roughly 0. Now, let's move to some theoretical consideration about both types of controller. We have seen that both the PD and PV controller consist of proportional and derivative action. But while on the proportional derivative controller, the derivative action is in the forward path, in the PV one it is in the feedback path. So let's consider a step reference. We can see that the only difference between the two controllers occurs at the step rise time t0. The proportional derivative controller is affected by derivative kick, which makes the system faster but also more nervous. In the PV controller instead, since the sharp changes of the set point is not taken into account, there is not the derivative kick. The system response is a bit slower but smoother. Moreover, in the real case, as we have seen, the difference in the controller command, which is caused by the derivative kick, is reduced by the saturation. Let's now consider a varying reference, like in tracking applications. Here we see that the behavior is different, since we can assume that the set point derivative is almost always different from 0. And let's focus on the derivative action of the PV controller. This action is proportional to the ball velocity but with a minus sign. Hence, it inhibits rapid movements of the ball, which is the characteristic behavior of a damper. At this point, the natural question will be, why do we have to add an integral action since we have already designed pretty good controllers? To answer this question, let's open Activate and let's run again the model with the PV controller. This time we introduce some disturbance, for example lifting the BBT on one side. We can see that the steady-state error occurs and the controller is not able to eliminate it. The steady-state error disappears only if we remove the disturbance. And if you try to do the same with proportional derivative controller, you will find the same behavior. Hence, both the PD and the PV controller can't reject disturbance and eliminate the steady state error. For this reason, in the next video, we will introduce the integral action. That's it for this video. If you would like to deepen your knowledge about system dynamics and controls, we encourage you to visit the first link. In the ebook, you'll find some of the topics we have covered today and many others. Moreover, feel free to share any questions you might have about Compose and Activate in the MBD forum. Thank you for watching and see you at the next video.